All righty, good morning, everyone. So, one more thing to talk about when it comes to potentials and all that good stuff are these equipotential surfaces or equipotential lines that we talked about in lab. Now, we talked about them in lab, so I'm not going to belabor this too much, but again, just kind of remind you that an equipotential line or equipotential surfaces are lines or surfaces. So lines in 2D, 2 dimensions, or surfaces in 3 dimensions, or 4 dimensions, or etc., where the potential anywhere along the line or surface is constant. Okay, so an equipotential surface or equipotential line is any line in 2D, again, or a 3D, it would be a surface where the potential is the same everywhere across that line or surface. Okay, so every particular point along that has exactly the same potential. So that's what we call equipotential lines or equipotential surfaces. Now, why we care about them, which is what I told you before, is because it tells us about what the electric field actually looks like. So kind of tell you a little bit about that. So let me draw a couple equipotential lines here. Let's say these are all lines, which are equipotential surfaces or equipotential lines, where they all have different potentials. So for example, let's say that the yellow one here is, I don't know, 3 volts. The orange one is 2 volts. And the blue one is 1 volt. Okay. Now let's think about what happens if I start off on one of these lines, let's say the 2 volts line, and then I move along some given path, and then I end up back on the 2 volts line. So let's say I move this way along this particular path, or I can just move along this green path here along a straight line. So either one, doesn't really matter. So let's think about it. So now what we know is the work done to move from one point to another point then is going to be equal then to what? Minus the change in potential energy, which is then equal to minus Q times the change in potential, which is then also equal to, as we know from yesterday, Q times E times the displacement. I'm going to write as delta Q times then cosine of the angle between the two. Now, because I start and finish on the same equipotential line, what then has to be my change of potential? 0. So what I know then is what? Even if I start off here and I go along the white line, which means I go off of this line and I touch the 3 volts, and then down here I go past 1 volt, so I'm like 0.7 volts or something. But as long as I start and finish on the same equipotential surface, what I know in this case then is that my change of potential must be equal to 0, which means that by this, the work then must be equal to 0. So for me to move my charged particle here, which has a charge of Q, along the equipotential surface, or at least along some path which connects 2 points along the equipotential surface, it does 0 work. I had to do 0 work to do that. Now this one's a little more complicated. I had to do positive work first, and then do negative work, and then positive work, and etc. But the sum net of the work that I do along the white line is equal to 0, as well as the green line. Green line is 0 the entire time. White line is a summation of both positive and negative works. Now, what does that tell us then? Well, that tells us then that this right-hand side must be equal to 0 as well. Right? So this whole entire thing must then be equal to 0. So what does this mean? So this gives us information about how the electric field looks like compared to the equipotential surface. Because this entire expression here is equal to 0, that means something here must be equal to 0. Right? So either the charge is equal to 0, which is not, or the electric field is equal to 0. But if the electric field was equal to 0, we wouldn't have equipotential lines. There would be nothing there, because as long as I have different lines here, I have to have an electric field, as we talked about, because as long as my potential is changing with position, I have to have an electric field. So it's not 0. The displacement is also not 0, because I go from this point to this point. So my total displacement is simply the entire length of the green line here. So this is my displacement. So that's also not 0. So the only thing here that can be 0 is the cosine curve, or the cosine portion of this. So what this implies to me then is that, well, cosine of theta must be equal to 0. This is the only thing which can be equal to 0. Now, for what values of theta is cosine equal to 0? What's that? 90 or 270, right? Or plus or minus pi over 2 or 90 degrees, right? As Logan said, 90 degrees or 270 degrees. So what this means then is that what? If I move along this equipotential surface, what this is actually telling me is how the electric field looks like compared to the equipotential surface. What it tells me then is that what? Since I'm moving along the equipotential surface, this is the direction of my displacements, the electric field then must be perpendicular to the equipotential surface along this particular equipotential surface, if I can speak. So this is telling me what the electric field actually looks like as far as the equipotential surface looks like. So the main point of this is that what this ultimately tells me is that the electric field must be perpendicular to these equipotential lines. Or again, or surfaces, if I'm working in 3D. So the beautiful part about these equipotential surfaces, which is what we learned from lab, was that as long as I know what the equipotential surfaces look like, I can then map out exactly what the electric field looks like, because I know it has to be perpendicular to these lines at any given point. Which means that if I want to know what the electric field looks like here, all I have to do is draw 90-degree lines here, and then simply connect these 90-degree lines to then determine exactly what the electric field would look like. So in this case, this would be an electric field line, this would be an electric field line, electric field line, electric field line, electric field line, because I know that the electric field has to pass through it at 90-degree angles. Now, what we also learned yesterday was that the electric field, magnitude anyway, say in the x direction, was then equal to what? The change in potential divided by the change in position, right? Or if I didn't look at the magnitude, and if I looked at the actual vector itself, it came in with a negative sign. What it actually said then was that the electric field in the x direction was then equal to negative the change in potential divided by the displacement. This negative sign then tells me the direction of the electric field, since the electric field is a vector, which means that it points from high potential down to low potential. So in this case, if I know what the equipotential surfaces look like, and I know the values of the equipotential surfaces, what I can do then is I can say, well, I know the electric field then has to be perpendicular to that, and it has to point from high potential down to low potential, which means my electric field would point in this direction. This is then my electric field. Okay. So this is the utility of the equipotential lines or these equipotential surfaces. Knowing these will tell me exactly what my electric field looks like in any given space. Now, as we started off this chapter, the beautiful part about potentials, though, is that potential is nice and easy to measure because all I need is a voltmeter. I can map these out by simply using a voltmeter. From that voltmeter, I can then establish exactly what my electric field looks like everywhere in space, unlike measuring the electric field directly, which is actually very hard. It's actually very hard to measure that. So this is the utility of these equipotential surfaces. This is what's so beautiful about them. So I'll show you a couple little simulations. So we're going to go back to that simulator that I was showing you the other day, but now we're going to play with the equipotential surfaces. Once the thing actually shows up. Okay. And then I'll draw a couple little things here, and then we'll move on and start talking about capacitors. So just to remind you, this is our dipole. So again, here's a dipole. So here are my electric field lines for my dipole. So I'm starting off with this. Now, what I could do instead is I could look at, instead of the electric field lines, what do the equipotential surfaces look like? So for example, this is the equipotential surfaces for my dipole. Okay. So if I draw that up here, I find my eraser, here it is. So this is the one that I drew on the board when it came to the lab. But what I have here is I have some charge particle here, some charge particle here. What happens in this case is I get kind of a circle around this guy, and then it starts to kind of open up. And I start getting things that look like this. Around this one, I also get a circle. So it does something like this. And I'm going to get something that looks like that, right? So again, here, since these are my equipotential surfaces, if I want to know what the electric field looks like, again, I'm going to start at some point, draw 90 degree, 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 and then I can connect these guys together to establish exactly what my electric field line looks like. All right. Now, from here, to know if which one is the positive charge and which one is the negative charge, I would then have to look at the values of these equipotential surfaces. So again, I'd have to know if this is 5 volts, 4 volts, 3 volts, and etc. Here, since I don't have any information about that, I only have these lines. The best I can say is, since this line starts here, terminates here, or starts here and terminates here, one of these has to be a positive charge and the other one has to be a negative charge. This is the best I can say. I don't know which one is which until I know exactly what the values of these equipotential surfaces are. In that case, then I know it would point from the high potential down to the low potential. In that case, if this was the high potential, this is low potential, then I know this is the positive charge and this is the negative charge. Because remember, positive is high potential, negative is low potential. So again, I can map out, again, exactly what the field lines look like by knowing these equipotential surfaces. And then we can look at all kinds of different other configurations. For example, the quadrupole. Let's look at different slicing. You're going to give me a slicing. Okay. Tricky. Okay. So for example, this is a different slicing. So this is just looking at a plane. So these are lines, not surfaces. But again, this tells me exactly what the electric field will look like when I draw these field lines. I'm going to look something like this. Let me take away the slicing. So it looks all pretty. So again, this is the beautiful part about equipotential surfaces. This is why we care about them so much, because as long as I know what the equipotential surfaces are, what they look like, then I can establish exactly what the electric field looks like and the direction of the electric field, as long as I know what's high potential, what's low potential. Everyone's okay? So next thing we want to look at is capacitors. So this will be our last topic in this chapter. So let's start talking about capacitors. So capacitors are also something we very briefly talked about in lab, but let's talk about it a little bit more. So capacitor is basically two metal plates separated by some distance. Let's call that D. So this is going to be some distance D, and I have two metal plates, which means that these are two conductors. So I have two conductors. Typically, what's inside of here is usually going to be air, but I can put other things in here as well. Those other things are what are called dielectrics, and we'll talk about that in just a little bit. But let's say for now, this is just empty space. So this is just what we call an air-filled or air-gapped capacitor. Then what we're going to do is we're going to take this capacitor and we're going to attach it to a battery. So this is going to be my battery, where this battery is going to have a potential difference. Let's call this delta V. Now what's going to happen? Now, when I hook this up, what we pretend is that positive charges start moving out through the positive terminal, and then they're going to start moving in this direction. Now, as I mentioned yesterday, this is actually absolutely wrong. It's actually negative charges which come out of the negative terminal and move in the opposite direction. Thank you, Benjamin Franklin, but whatever, we're going to pretend. So it's going to be great. So what's going to happen then is I'm going to take one charge here. I'm going to start moving that through, and I'm going to deposit that guy onto my positive, well, onto the neutral plate initially, so that this thing becomes positively charged. Simultaneously, what happens over here? Exactly, the positive charge on this side is going to get scared because this positive charge showed up, so he's going to actually start moving away, and he's going to move through and go back inside of the battery. Right? Now, initially, for me to move this first charge here costs me no work, because initially this has no potential difference across it. So I'm basically moving this guy onto here where there's no potential difference. So I did zero work, right? Now what I'm going to do is the battery wants to keep going though. So now it's going to take a second charge. So here's my second charge. and it's going to try to move this charge then onto this plate, right? Well, what happens in this case though? So now I'm trying to put a charge onto a plate which now already has a charge. Is it going to do it freely? No. What I now have to do is the battery now has to do work onto this charge, to force this charge onto this plate because it has a Coulombic repulsion between the two. Right? So as we talked about yesterday, what happens is the electric field itself doesn't want it to be here because it only wants a negative charge here, not a positive charge. So the work has to come from an external agent, where the external agent in this case will be the battery. This is the point of the battery. So the battery then is going to deposit this positive charge on here, kicking off a positive charge from here, putting it back into the battery, right? But this time around, I had to do a small amount of work, right? I didn't get to do it for free. Let's keep going. Now I'm going to take a third positive charge, bring this and try to put this guy onto the plate itself. How much work did this one cost me? At least, right? It's going to be a huge amount of work, at least bigger than the original amount of work, because now I have two trying to repull it, and etc. So eventually what's going to happen is, again, I'm going to put this one on here. I'm going to kick off the positive charge from here. I'm going to bring that back into the battery. And then eventually this is going to keep occurring until eventually what's going to happen? Exactly. The amount of work that the battery will be able to do will no longer be able to overcome the amount of work it will take for me to put another charge onto here, which means this is going to stop. Once this stops, what happens then is that this thing is going to reach a maximum positive charge. Let's call this guy Q. And this side is going to reach a maximum negative charge, negative Q, where these two guys will be charged exactly with the same amount of charge, except opposite in magnitude. So this is a capacitor. So the capacitor then is what? This guy and this guy here. Right. Again, when I hook it up to a battery, eventually what's going to happen then is that this guy's going to reach a charge of Q. This guy's going to reach a charge of a negative Q. And then the potential difference across this will then be exactly equal to the potential difference across the battery. Okay, so those two will be exactly the same. Now, what happens? So now if I plotted the amount of charge on the plates versus the amount of potential I supply by the battery, what we find in this case then is we actually get a nice straight linear line, meaning that these two guys are linearly proportional to each other, where the slope of this line is what's called C, which is equal to the capacitance of the capacitor. Capacitance of a capacitor. So you can think about the capacitor or the capacitance of the capacitor as basically the amount of charge that can be stored based off of the amount of potential. Basically, what you can kind of think about that. So mathematically, what this says then is that the charge on the capacitor plates is then equal to the capacitance of the capacitor times then the change in potential, or the potential difference across the capacitor. So this delta V here is specifically the potential difference across the capacitor. And then Q here is simply equal to the charge on the capacitor. In this case, the positive charge on the positive plates. So from this, we can then say that the capacitance of the capacitor then is simply equal to the charge divided by the potential across the capacitor. So this is actually the formal definition of capacitance. Now from here, we know that charge has units of coulombs. This has units of volts. So this is actually a coulomb per volt, which gets its own name, which is known as a capital F, which is what's known as a farad. So the units of a capacitor are what are known as farads, which is actually a coulomb per volt. And so this is what we call a farad. Now, what are capacitors used for? Well, we use them actually in electrical objects all the time. So for example, your cell phones will have these, computers have these, pretty much almost most electrical equipments will have them. They're used for all kinds of different things. So for example, inside of my computer, capacitors are RAM. These are your ones and zeros. Okay? So basically what happens is your RAM is built up of a whole bunch of different capacitors, and then you fill some of these capacitors. So basically you put a potential difference across it so they have charge, meaning they have a potential difference. Some of them you don't put a potential difference, so there is no charge. And then you read that as your RAM. So basically your ones and zeros come from, is this guy charged or is it not charged? Then by having those guys, then you can read your RAM, and then that is the temporary memory inside your computer. What's up? Mhm. Oh, so the capacitor, the capacitance, we'll get there in a second, but that's fixed by the geometry of the capacitor. So every capacitor that we create, so for example, those ones that you used in lab, this can only have a certain amount of capacitance to them. So the charge is fixed by the potential based off of the capacitance, but the capacitance is based only off the geometry of the capacitor. So if I need a certain amount of capacitance, then I have to construct the capacitor in such a way to actually create that amount of capacitance. So like a physical capacitor will actually typically be two pieces of aluminum foil, basically, with a piece of paper filled in between them. That's the dielectric. We'll get there in a second. Rolled up into a nice cylinder and then stuffed inside of that little thing. Basically the way it is, but well, that's right. But it turns out, we'll get there in a second, is that the capacitance of the capacitor is actually only determined by the geometry of the capacitor, not by the potential or the charge. So the charge is fixed by the potential, but not the capacitance. Great question. So, so that's one example of what we use capacitors for. Those are your RAM. Anybody have a surge protector in their house? Those are also capacitors. So basically that's just a series of capacitors. So if your house got struck by lightning, you get a huge surge of charge moving through, which means that you have a huge amount of current. These capacitors then would eventually block this current because it would build up the charge on the capacitors, which would block the current, which means that you wouldn't get a huge surge of currents inside of your computer and fry your computer. Right? This is the point of those. So we use these a lot. So those are your kind of main ones that they're used for, but they're used in other things as well. But we use these things in electrical circuits all the time, and that'll be the subject of exam 3. So we're going to start looking at electrical circuits and all that kind of good stuff. So great. So that's right. So the formal definition is this, and we're going to see that, as Logan basically asked, it turns out that this thing is actually dictated only by geometry. We're going to see that in an example. So let's talk about how we would actually calculate the capacitance. So the way you would actually calculate the capacitance is, most of the time, unfortunately, you have to do this. You have to experimentally verify what it actually is by building a capacitor, applying a battery to it, and then measuring the charge, doing that for a few points, finding the slope of the line, and find the capacitance. This is if it's not geometrically nice to work with. But it turns out in some cases, we can actually find, for nice simple geometries, what the capacitance is based off of geometry. So let's do an example of that, and let's see how we would actually calculate the capacitance for a nice system. So nice simple geometry. And that nice simple geometry is basically just going to be the parallel plate capacitor. So let's look at our parallel plate capacitor. Nope. So what it wants us to do is find the capacitance of this particular parallel plate capacitor. So let's say here's our parallel plate capacitor. So we have 2 sheets of charge, which are separated by some distance of d. And let's say that the bottom portion is my low potential, so that's going to be my negative. And then the top one is going to be my high voltage or high potential. So this is going to be my positive. So this one's going to have a charge of negative Q down here, and then positive Q on the top. So good. So to find the capacitance of this capacitor, we now know that the capacitance is equal to the charge divided by the change of potential, which means the only thing we need to do now is first find the potential difference across the capacitor. So what is the potential difference across the capacitor? So let's do that. So we know that, based on what we just wrote, is that what? The electric field magnitude is then equal to the change in potential divided by the change in distance. Now, in this case, what that means then is that the electric field going from up here down to here. So remember, electric field points from the positive side to the negative side. Here's my electric field. The distance going from this side to this side is simply going to be this distance of d. So what this tells me then is that this is going to be equal to my change of potential divided by the distance then between the two plates. Okay. From here, we can then find that what our change of potential across the plates is simply going to be equal to the magnitude of the electric field times the distance between the two plates. So this is my potential difference. The other thing we know is that what, since these are two effectively infinite sheets of charge, we know the electric field inside of the plates is equal to sigma divided by epsilon naught. So this is the other thing that we know. Something else we wrote down a while ago. So this tells me then that my potential across the plates is then equal to the charge density divided by epsilon naught times the distance. But remember that sigma, which is the charge density, is equal to what? Anybody remember what sigma is equal to? The charge per unit something. Over area, good. So this is the same thing as the charge on the positive plates divided then by the area. So let's put all this stuff together. So finally, this is going to become equal to the charge times the distance divided by the area times epsilon naught. So this is my potential difference across the plates. Now let's take this guy and put it in here. So this thing finally says that the capacitance then is going to be equal to the charge divided by the charge times the distance divided by the area times epsilon naught. What happens to those two charges? They cancel, they're the same. So finally, this is going to move to the top. So this becomes the area times epsilon naught, all divided by the distance. So this is the capacitance of our parallel plate capacitor. Now, what's interesting about this, and this goes back to what Logan was basically asking, what this tells me then is that the capacitance of the capacitor, at least for the parallel plate capacitor, only depends on two things. It only depends on the surface area of the capacitor, and it depends on the distance between the two plates. That's it. It doesn't depend on the charge. It doesn't depend on the potential. The only thing it depends on is the geometry of the plates themselves. This turns out to be true for any type of capacitor. So what we ultimately learned from this is that the capacitance of the capacitor only, keep breaking my talk, depends on the geometry of the capacitor. Which means that what? If I change the geometry of the capacitor, then we change the capacitance of the capacitor. But if I change the potential or if I change the charge, the only thing that happens is when I change the potential, that changes the charge across the capacitor. It doesn't change the capacitance of the capacitor itself. So the capacitance of the capacitor is only fixed by the geometry of the capacitor. If I change the geometry, then I change the capacitance. That's the only way I can actually change the capacitance. So another simulation here. So here, what I have is what? So here is a battery connected to a parallel plate capacitor, which initially has some area and some separation distance between the two. So initially, this is showing me the capacitance of my capacitor for this particular geometry. Now, let's hook this up to the battery. So let me turn this thing on. If I can get it to work. There we go. Okay, so it's finally turned on. Let me put my probes across the actual plates here, so we can measure the potential difference. So right now I have a 1.5 potential difference across here equal to that of the battery. This thing has some charge. What's the charge? So my charge in this case is 0.13 times 10 to the minus 12 coulombs. And this has a capacitance of 0.89 times 10 to the minus 13 farads. So now let's start changing and playing with the geometry. So what this thing says then is what? If I increase the surface area of the plates, what should happen to the capacitance? Should it go up or should it go down? If I increase the area? gonna go up, right? So this thing is linearly proportional to the area, which means if I grab this guy and I make a bigger area, you can do it. There we go. What happens in this case then is that I have now increased the capacitance. And since I have increased the capacitance, I have also increased the charge. Right? Again, in this case, since this is fixed by the battery, since I increase the capacitance, I have simultaneously increased the charge. Now, if I decrease the distance between the plates, what would happen to the capacitance? Also going to go up, right? So now if I take this thing, push it, you can do it. There we go. Make this smaller. So I'm going to put this over here. So we know the potential difference, still 1.5 volts. But again, what happens in this case then is what? So now I have changed the capacitance, which has also then changed the charge. Right? So the only way to change the capacitance of my capacitor, again, is to change the geometry. So the capacitance only depends on geometry. And that's it. Is okay? So what is the overall point of a capacitor? The overall point of a capacitor is to store energy. This is the point of the capacitor. So a capacitor is added to a circuit, which we'll discuss those things in length soon, to store energy for later use. So this is the entire point of a capacitor. So we put capacitors into circuits to store energy for later use. And the way that it actually stores energy is it stores energy by the work. The amount of work that it takes to fill up the capacitor based off the battery is then stored inside of the capacitor as stored up potential energy from the work of the battery. Right? So what this means then is that what the work done by the battery is then equal to the potential energy stored within inside of the capacitor. So we can then ask the question of, well, how much energy is actually being stored? Well, it turns out the amount of energy which is being stored is actually equal to 1/2 the charge across the capacitor times then the potential across the capacitor. So this is actually the amount of energy which is being stored by the capacitor. Everybody's okay? Now, what we can also use, though, is this guy and then rewrite, for example, the charge as then being the capacitance times the change of potential. So I could also rewrite this then as 1/2 the capacitance times the change of potential squared, right? By simply replacing the charge by the capacitance times the potential. Or I can replace the voltage by being the charge divided by the capacitance. So this is also equal to 1/2 the charge squared divided by the capacitance. So this is actually the amount of energy which is being stored by the capacitor. Any one of these three is exactly the same thing. The only thing that this thing is saying is three different things. This one says that the energy which is being stored inside of the capacitor is actually stored in the potential difference across the capacitor. This one says that the energy which is being stored inside of the capacitor is actually stored in the charge, which is placed on top of the plates. And this one says the combination of the two. It's actually stored within inside of both. This is the amount of energy which is actually being stored inside of the capacitor. Okay, so this is the amount of total energy which is then being stored. So another way we can define this, one other way we can look at it is to define something else, which is what's known as the energy density. So let's talk about the energy density real quick. And then we'll move on to dielectrics, and then we'll do some examples of all this stuff. So what's energy density? So the energy density, we're going to write that as a little u sub E is actually equal to the potential energy stored per unit volume. Right. So this is the energy density. So basically, it turns out that if you put all these things together and then you replace some things, I'll just kind of skip all the math for you, but it turns out this thing ends up being 1/2 equal to epsilon naught times the magnitude of the electric field squared. So this is what's known as the energy density. So again, basically all you're doing is you're taking this, you're rewriting the capacitance as parallel plate capacitor, you're rewriting the change of potential like we did earlier, which is simply the electric field times the distance between the two, dividing by the volume, and then you end up with this thing. So what does this thing say? What this thing says is that when we have our parallel plate capacitor, so here's my positive plate, here's my negative plate. Again, we know the electric field points from the positive charge to the negative charge. So this is my electric field. What this thing is basically saying is that the energy is actually stored within inside of the electric field itself. And this is the amount of energy stored per unit volume, which basically means that if I went in here and I cut out a small volume, so this is my volume of V, then this is the amount of energy that would be stored within inside of this volume. That's what this thing is telling me. So it means that if I have this volume V, then I simply take this thing, multiply by that volume, and that's the total amount of energy which is being stored. Okay. So this one says that the energy is stored within the electric field. This one says that it's stored within the potential difference. This one says that it's stored within the charge. And this one says both. So these are basically 4 things that all say the same thing. So this one just has the viewpoint that it's actually stored within inside of the electric field. So in this case, I would go inside the electric field between the plates. This is the energy stored in a volume and inside of here. This one says that it's actually stored on the charge of the plates. So if I increase the charge, I increase the energy stored. This one says it's increased within inside the potential difference across the plates, which again says if I increase the potential difference, I increase the amount of energy stored. And this one says, well, it's a combination of the two. So it's between the charge and the potential. But again, these all say exactly the same thing. Now, which one do I use? Well, which one I use just depends on what I know. If I know the capacitance and I know the potential, I'm going to use this one. If I know the charge and I know the capacitance, I'm going to use this one. If I know the charge and I know the potential, I'm going to use this one. It all just depends on what it is that I know, but they all, again, say exactly the same thing. Now, another way, it turns out, to actually increase the amount of capacitance to store more energy on a capacitor is to add something in between the capacitor plates. This something that we add is what's known as a dielectric. Let's talk about dielectrics real quick. So, a way to increase the capacitance of a capacitor is to add a dielectric between the capacitor plates. Like I mentioned earlier, a physical capacitor pretty much is just aluminum foil with a piece of paper in between the two. That piece of paper is the dielectric, okay? So what's the point of the dielectric? The point of the dielectric is to increase what's known as the potential breakdown. So let's talk about potential breakdown. So what is potential breakdown? So imagine it's the winter time. Scuffing your feet all day, right? It's gonna dry out, right? Not like it is now, nice and humid, but let's say it's dry. And then you go to reach for this door handle, and then what happens? You get a shock, right? Why do you get a shock? This is what's called potential breakdown. So the reason you get a shock is because now you are charged, kind of walking around picking up charges, right? Being dry, so those charges are not jumping off you from the air, right? As we talked about before. So we don't have all that humidity to take it away. So now you are walking negative charged object. You go to grab the door handle. What is the door handle made of? Metal. Metal is what? It's a conductor. So what happens to the negative charge particles inside of the door? So my hand gets close to it. My hand is negatively charged. Where do those negative charges go? They move away, right? So what's going to happen is it leaves then the door handle itself positively charged. So now when I'm reaching for it, I have now created a capacitor. This space between your hand and the air, or in the door handle, is now a capacitor. So what happens then is the closer and closer and closer I get, the greater the potential difference becomes between my hand and the door handle. What eventually happens? What eventually happens then is the potential difference between my hand and the door handle exceeds the amount of potential difference that air is allowed to have. What this does then is it breaks down the air, hence potential breakdown, such that the air then becomes ionized. You physically strip off electrons from the air, causing the spark, because you have now ionized the air. This is what's called potential breakdown. So you have reached and exceeded the ability for air to support the potential difference between your hand and the door handle. Now, the dielectric, which is actually an insulator, so dielectric is actually just a fancy word for insulator, is put in there because the potential breakdown of the dielectric or of the insulator is greater than that of air, which means you can support more potential difference between my hand and the door handle by putting in some sort of insulator. Right? So in the wintertime, that would physically be me carrying around a screwdriver, which has a plastic handle. In this case, if I want to touch the door handle and I don't want to get shocked, I would take my screwdriver with the plastic handle and I would simply touch the door handle. Do I get a shock in this case? The answer is no, because the potential difference or the potential breakdown of the plastic inside of the screwdriver is much higher than that of air. So just all the charges for me are going to go into the door handle, and then I can grab the door handle and open it without getting shocked. Beautiful. So the point then of the dielectric is to increase the potential breakdown of the material itself so I can put more potential onto the system. By putting more potential onto the system, I can then add more charge, and then I can store more energy. So this is the point of a dielectric. So the dielectric does is it actually increases this potential breakdown. And it does this by a factor of what's known as the dielectric constant. So let's talk about the dielectric constant. So the dielectric constant is equal to another K value. We love Ks. This is going to be a constant based off of the type of material that the object is. So if I tell you it's plastic, I have to tell you the dielectric constant of plastic is like 2.5 or something. But this is basically going to be a number which is greater than 1. Okay, so this is going to be a number greater than 1. And this is basically just equal to the ratio of the breakdown potential of the dielectric to the breakdown potential of air. This is what the dielectric constant actually is. It's the ratio of the breakdown potential of the dielectric to the ratio of breakdown potential of air, which is just going to make this some number, which is a unitless number, because this is the potential divided by potential, which means it has no units. So this is a unitless quantity. Now, what effect does this have on the capacitor or the capacitance of the capacitor? What this ultimately does is it just increases the capacitance of the capacitor by the factor of the dielectric constant. So this means that when I add in the dielectric, I get a new dielectric constant. Let's call that, or sorry, I get a new capacitance. Let's call that C prime, which is equal to the capacitance of the capacitor times the dielectric constant. So I'm going to write that as C0, where C0 is the original air-filled capacitance. So this is when it's air-filled. And this is when it has the dielectric. So the point of putting in the dielectric is to increase the capacitance by a factor of the dielectric constant. This is what it physically does. All right. Is open? K is always going to be greater than 1. Air is the minimum. That's right. So the only time it would be equal to 1 would be with air. In that case, K would just be 1, and then these two things would just be the same. Exactly. You'll never have a scenario where K is less than 1. Or you can probably manufacture something that's less than 1, but in reality, just usually never. Now, the overall effect on the circuit then, and how much energy it stores, actually depends on how we add the dielectric. So what is the effect of all this on energy storage? So what is the effect on energy storage? Well, this is ultimately going to depend on how I add the dielectric to the system. And there's basically 2 different ways that I can do this. I can add the dielectric when it is disconnected from a battery, or I can add the dielectric when it's connected to a battery. These are my basically 2 choices. So let's look at each one. So let's say here's my capacitance. So let me bring up some things here. So I have a capacitance here. Look at the plate charge, energy storage, and also the voltmeter. Okay. So here it is where this thing is what? Dielectrics on the outside. And what I'm going to do is let's connect it to the battery, but I'm going to put a voltage on here. Okay. So now this thing is going to be connected. I have a voltage. So this thing is going to do what? So it's going to have a potential difference. Measure my potential difference of 1.5 volts. This thing has a what? Charge. It also has a capacitance. Now let's leave it connected to the battery and let's put in the dielectric and see what happens. All right. And we'll talk about this. So now I'm going to take this guy. I'm going to push it inside. Hopefully you can do it. There we go. Now let's talk about what happened. So first things first is we see that the potential difference across the capacitor plates is still the same. And the reason it's still the same is because it's connected to the battery. It can't do anything other. So when it's connected, first thing we find out is that the potential, the new potential, is equal to the original potential. So nothing actually changes. But what has happened? So here we see that what? The capacitance has actually gone up. Because again, if I pull this thing out, here's the capacitance. But if I put it in, see in this case, the capacitance is actually shot up. The charge is actually shot up. And the energy storage is actually all going up as well. All right. So what happens in this case is if I add the dielectric to the capacitor while it's connected to the battery, the potential difference does not change, but the capacitance increases by a factor of the dielectric constant. The charge across the plates also increases by a factor of the dielectric constant. And the energy, which is stored, also increases by a factor of the dielectric constant. So these are the effects of adding this guy. And so when I add it, what happens is the potential stays the same. Capacitance increases, the charge increases, and the energy storage increases. Now, let me pull this guy back out. Ooh, pulled it a little too far. Move over. Thank you. Okay, so now I'm going to disconnect it from the battery. So now I have a 1.5 volts across here, but now it's disconnected to the battery. All right. Then we'll talk about the difference between the two. So now what I'm going to do is I'm going to put this guy back in and let's watch all the same quantities again. So already I have a kind of a mental picture of, so now let's put this guy in. So first thing we note is that what? The potential went from 1.5 down to 0.3. So what actually happens in this case is that the potential difference actually decreases, and it decreases by an amount of the dielectric constant. Now, the other interesting thing that happens is actually the charge across the plates stays exactly the same. We'll talk about that in just a second, why that actually makes sense. So that stays the same. And notice what happened to the capacitance and what happened to the stored charge. So the capacitance still went up. It went up by a factor of the dielectric constant. However, what happened to the stored energy? It went down. In this case, that's the stored energy. Went down by a factor of the dielectric constant. So the effect of adding the dielectric depends on if it's connected or disconnected. All right. So again, if it's connected, what happens is the potential stays the same. And the reason potential stays the same is that the potential is being supplied by the battery. Since I haven't changed the battery, then I have to have that same exact amount of potential difference. Capacitance goes up, energy goes up, and charge goes up. In this case, potential goes down, but the charge stays the same. So why would the charge stay the same? Exactly. There's no way to go back into the battery or have more charge come from the battery because it's not connected to the battery. Since these two plates are not connected to anything, whatever charge they had initially, the charge has to stay there because it can't spontaneously add charge or subtract charge because it can't come from anywhere. So in that case, the charge has to stay the same because the charge just can't go anywhere. So since the charge has to stay the same, that then decreases this guy increases to then cause this guy to decrease. That's okay. So again, since the charge stays the same, potential has to decrease by the same amount that the capacitance increases to keep that proportionality the same. So these are dielectrics. So again, the point of the dielectric is to increase the capacitance of the capacitor by a factor of this dielectric constant. That dielectric constant depends on the material that I put inside of it. So again, if I put paper in there, or if I put plastic in there, if I put glass in there, whatever it is that I put in there that's a dielectric, will have a different overall dielectric constant, but it's simply a constant. The unit is constant. The effect that that has is going to depend on if it's connected or disconnected. All the material. No, great. So let's do a few examples of all of these different things just to kind of reinforce all this stuff. And then we'll, I guess, do a review, hopefully. Try to make sure there's enough time. Okay, only 2 examples, I guess. But so the first one says that it wants us to calculate the capacitance of the parallel plate capacitors whose capacitance or whose plates are 20 centimeters by 3 centimeters and separated by a 1 millimeter air gap. All right, so let's draw one. All right, so we have our parallel plate capacitor. So it has a cross-sectional area of A separated by a distance of D. So my area was equal to, so what are the sides and everything? Okay, so 0.2 meters by 3 centimeters. So 0.03 meters. And what's the 1 millimeter? Okay, so it's going to be 1 times 10 to the minus 3 meters. Good. And that's all I need to know. Good. So first thing I want to know is part A, what's the capacitance of this guy? So we know the capacitance now is equal to what? Epsilon naught times the area divided by the distance. So good. So this is then going to be equal to epsilon naught, where epsilon naught is 8.85 times 10 to the minus 12. And this has units of coulomb squared per Newton meter squared. Times in the area, which is that 0.2 times 0.03 meters squared. So that's going to kill off this meter squared. All then divided by what? The distance, which is 1 times 10 to the minus 3 meters. Look at my numbers. What I find in this case then is, once I get there, that this works out to be about 53 times 10 to the minus 12 farads, which we can write as 53, what's called picofarads. So pico is 10 to the minus 12. So this is the amount of capacitance of my capacitor. So pico is 10 to the minus 12. It's okay. Nice and simple. What's part B? Part B then says, what is the charge on each plate if a 12-volt battery is connected across the 2 plates? Well, we now know that the charge is equal to the capacitance of the capacitor times the potential difference plus the capacitor. So in this case, we now know the potential difference is simply 12 volts. We know the capacitance is 53 picofarads. From there, we can find the charge. So this is then going to be 53 times 10 to the minus 12 farads times then 12 volts. Look at my numbers. What I get in this case then is this works out to be about 6.4 times 10 to the minus 10 coulombs. So this is my charge. What's next? C then says, what is the electric field between the plates? Well, we now know that the electric field is equal to what? The change in potential divided by the distance between the plates. So this is the magnitude of the electric field. This is equal to the change in potential divided by the distance. We know the change of potential, that's simply 12 volts, because that's what's supplied across it based off the battery. We know the distance is simply 1 millimeter. So this is then going to be 12 volts divided by 1 times 10 to the minus 3 meters. So plug in my numbers, this works out to be about 1.2 times 10 to the 4th volts per meter, which is the same thing as a Newton per coulomb. Those two things are the same. Finally, the last part then says, estimate the area of the plates needed to achieve the capacitance of a 1 farad capacitance given the same gap distance of 1 millimeter. Okay, so basically, this wants us to say, okay, what we really want is the capacitance of this thing equal to 1 farad. Right now, we have 53 picofarads. So we have to increase this thing by 1 times 10 to the 12th, basically, right? So from there, it wants us to find out what is the area necessary to make this thing equal to that. So good. So from here, we're just going to start off with this definition again. So for part D, we know the capacitance is equal to what? Epsilon naught times the area divided by the distance. From here, we want the area. So that means the area then is going to be equal to the capacitance times the distance divided by epsilon naught. Capacitance in this case is simply 1 farad times the distance is 1 times 10 to the minus 3 meters, all divided by epsilon naught, which is 8.85 times 10 to the minus 12. Plug in my numbers. What I find in this case then is this works out to be about 10 to the 8th meter squared. This is the area required to build a capacitor separated by a distance of 1 millimeter. So we're talking about that, right? About a millimeter. So if I wanted to build from 2 simple sheets, a 1 farad capacitor separated by a distance of this much, the plate area would have to be about 10 to the 8th meter squared. How big is that? Basically the entirety of Boston. So if I wanted to make a simple parallel plate capacitor, which had 1 farad worth of capacitance separated by a distance of 1 millimeter, the size of these plates would have to be the size of the entirety of Boston. This is why computers used to be in entire rooms. We just didn't have all the manufacturing things we have now to be able to make it down to smaller sizes. Okay? So this is why, yeah, this entire room back in the day was a computer that could do less than your graphing calculator. Definitely less than your cell phone. Sorry. So just to put that in context. So anyways, let's do, and I got one more example. So let's do one more example. So this involves a lot of the things that we've been talking about here. So this has a parallel plate capacitor, which is filled with a dielectric, which has a dielectric constant of 3.4. It's connected to a 100-volt battery. So after the capacitor is fully charged, the battery is disconnected. The plates have an area of 4 meters squared and a separation distance of 4 millimeters. Great. So let's write all that down. So good. So initially, here is my parallel plate capacitor, where we know the area is 4 meters squared. The separation distance D is equal to 4 millimeters. And then this thing is initially connected to a battery, which has a potential difference equal to 100 volts. But then we're going to disconnect it from the battery. So this thing is just charged and disconnected from the battery. So good. Then it says, find the capacitance, the charge on the capacitor, and the electric field strength in between the plates, and the energy stored in the capacitor. So we'll look at a lot of the things we just defined. Let's look at all this stuff. So for part A, first thing we want to know is what is the capacitance? Well, we know the capacitance again is going to be equal to, for a parallel plate capacitor, epsilon naught times the area divided by the distance. So it's going to be our 8.85 times 10 to the minus 12 times the area, which is 4 meters squared, all divided by 0.004 meters. So basically this 4 is going to cancel this 4. Meter will cancel that one. Multiply everything out. So this is going to be, so this will be 3 to the top. So it should be what? 8.85 times 10 to the minus 9. Right. Assuming I can do simple math. I think that is too much of a truth. Oh, I forgot the dielectric constant. Sorry, we have a dielectric, don't we? So we have to put a K on here. Times 3.5. There we go. All right, I forgot it had a dielectric in it. Sorry about that. So it has a dielectric, so we have our dielectric constant inside of there. Good. So this works out to be about 3 times 10 to the minus 8. There we go. Sorry about that. Please, I forgot I had dielectric. Hopefully I wrote that in. There we go. So we got a dielectric on the inside. Dielectric constant 3.9. Good. Or 3.4. Sorry. Okay. That's capacitance. Next thing we want is the charge. So we would then find the charge. We know the charge is equal to the capacitance times the potential across the capacitor. We know the capacitor has a potential of 100. So this is just going to be this number times 100. So this is going to be 3 times 10 to the minus 6 coulombs. So this has about 3 microcoulombs on it. 3 microcoulombs. Okay. Let's keep going. The next thing is what? The electric field. Yeah. So the electric field. So again, we know the electric field magnitude-wise, though, is equal to what? The change of potential across the plates divided by the distance between the plates. So this is just going to be 100 volts divided by 0.004 meters. So this works out to be about 25 kilovolts per meter. And this is my electric field. And then finally, the energy stored. Yeah. So we know the potential energy stored is either equal to 1/2 the charge times the change of potential, 1/2 the capacitance times the change of potential square, or 1/2 the charge square divided by the capacitance. Again, whichever one we decide to use, it doesn't really matter. It just depends on what it is that we know. In this case, we know pretty much all of those things. We know the capacitance, we know the charge, we know the potential. So which one do you want to use? The first one? Okay, great. So let's use the first one. So this is then going to be equal to 1/2 the charge, which was what? 3 times 10 to the minus 6 coulombs times the potential, which is 100. So it's going to be 1.5, and then I get a 10 to the minus 4, right? So it's going to be 1.5 times 10 to the minus 4 joules. Oh, we would only divide by the dielectric if we put it in So that would only be when we're putting it in, when it's connected to the battery, or when it's not. So the point is here, we already had the dielectric in and then we charged it. So it's not that we charged it and then put the dielectric in. So in that case, you'd be absolutely right. We'd have to divide, but we're getting to that point in a second. So good. Great. Everybody's okay? So the next part then says the dielectric now is carefully removed. So now we're going to take it out instead of adding it to it. So now it wants us to find all the new values of all of this different stuff. Yeah, so let's do all the new values of everything. So basically what's going to happen now is I'm going to pull out this dielectric without changing anything. So basically what we want to now go to the scenario where this thing now has our plate. So this is still A is equal to 4 meters squared. This is still D is equal to 4 millimeters. But now we're going to pull out our dielectric. So now our dielectric is going to be over here. Okay. So what that's going to do is it's going to change most of these quantities. So we want to know then is by how much is it going to change each one of these quantities? So this is what we want to know. So good. Let me find a place to write. I guess I'll start off here. So part B, we now want to know what's the new capacitance of the capacitor. Okay. Now what we said before was that what? Adding the dielectric to the capacitor increased by a factor of the dielectric constant. So now if I remove the dielectric constant, what should it do to the capacitance? Right, it's going to bring it back to the original or decrease this by a factor of the dielectric constant. So this is now going to be equal to this original divided simply by the dielectric constant. So basically all I'm going to do is I'm going to take this thing, divide by this 3.4, which should bring me back to this original number. So this is then going to be equal to 8.85 times 10 to the minus 9. This is going to be my new capacitance. Okay. Next part we did was the charge. Now, what should happen to the charge? Stays the same, exactly right. So in this case, the charge stays exactly the same because again, there's no place for the charge to go. So the charge has to remain the same. So this is still going to be equal to our 3 microcoulombs. Good. Now, what about the electric field or the potential, I should say? So let's do the potential first, and then we'll talk about the electric field. So what would happen then to the change in potential? So now what I'm doing is I'm pulling out the dielectric constant. So what we saw before was that what? If I move the dielectric constant in, what happens to the potential? Did it increase, decrease, or stay the same? It decreased, right? But now if I pull it out, what should happen? It should increase, right? It's going to do the opposite thing, which means that this guy is going to increase by an overall factor of the dielectric constant. So it means initially I had 100 volts. This thing is now going to be what? 340 volts, because I'm going to multiply that by 3.4. Okay. Good. What does that do to the electric field? Well, it doesn't change this number, but it changes this number. So all it's going to do is it's going to increase the electric field also by a factor of the dielectric constant. So in this case, the magnitude of the electric field is then going to be equal to what? K times the original electric field. So cool. So plug that in. So all I'm going to do is I'm going to take what 25 times 3.4, which works out to be about 85, I think. Yeah, 85 kilovolts per meter. So this is my new electric field. And finally, we want the new energy stored. Now, again, what we said was that's what adding the dielectric constant in, did it increase, decrease, or keep the energy stored the same? It decreased, so what should happen now? It's just going to increase by that. So what should happen now is that the potential energy, or the energy stored, is now going to be equal to the original, but now times the dielectric constant. So all I'm going to do is take the 1.5 times 10 to the minus 4, and then multiply that by 3.4. And then what I find in this case then is, lo and behold, my fingers will work, about 5.1 times 10 to the minus 4 joules. So this is my energy stored. Oh, that's it. We have all the tools. Got 6 minutes. We have options. So I can talk about what to expect and then do a quick video and throw that up online for you guys about all the equations. Or I can just write down all the equations and probably not have enough time to talk about what to expect. Which one do you want to do? Well, I found this guy. Okay, and then I'll either send you guys a sheet with the equations on it or just make a quick video with all the equations or whichever. I'll make sure everybody gets it. So let's talk about what to expect. So basically the format and everything's going to be the same. So let's talk about what to expect. So one problem I will tell you will basically deal with all this kind of stuff here. So basically it's going to have parallel plate capacitors, dielectrics, and then changing geometries. So basically, so one long problem. Long problem number one will be, again, parallel plate capacitors. Geometry of those. So again, changing areas and distances and all that kind of good stuff. So all the things we talked about and dielectrics. One other thing this one is going to talk about is actually, again, work. So this is going to have to do with work. So basically what you'll have to do is either change a geometry or add in a dielectric or maybe both. And in that case, you'll have to find out how much work was done to do that and who did the work. So meaning that if you're looking at the work from the viewpoint of the electric field, remember, this is going to be equal to negative of the change of the potential energy. Now, in this case, we're talking about potential energy stored by the capacitor. So in this case, looking at the change of potential energy, which is being stored. Now, again, if this comes out to be positive, who did the work? The electric field. If it turns out to be negative, who did the work? An outside agent, exactly. So again, if this is positive, that means the electric field did it. If it turns out to be negative, again, that means something else did. So all that'll be all kind of part of one problem. So just kind of walk you through a lot of these calculations we just did. So not too bad. The second long problem will actually involve, do it this way. So force by the electric field. So what do I mean by that? So what I mean is, again, you're going to know the electric field. You're going to have some charge there. And then from that, you'll have to find a force. A good example of this is, of course, our beautiful parallel plate capacitors, where we took a charge of Q, mass of M, sent it with some initial velocity inside, and then we watched this guy curve, right? So this would be a nice example of this. So basically something kind of similar to this. Now, this is also going to have things about potential in it. So this will have things about potential, mostly potential difference. Things you'll want to know for this are, if I remember correctly, again, the magnitude of the electric field inside of here is going to be sigma over epsilon naught. And remember what high potential means and what low potential means. i.e. what's positive and what's negative based off of that. And yeah, so this will walk you just through some things with that. Okay. Short problems, those will be things like potentials between point charges, electric field from point charges, all that kind of other good stuff. So, but the long problems will be basically these types of things. Okay. Is okay? Good, I got 1 minute left. I finally gonna give you your test back. So overall, I was pretty happy. The first part, short answer part, went really well for most people. First question went really well, and then second question not so great, but that's okay. It's okay. overall, I was really happy. I think the average was a 70, like a 70.5 or something like that, which not bad. Actually, see, it's a little bit higher in the summer, but that's okay. Okay. And the highest was a 94 without extra credits. So, but again, all these values are without extra credits. So, what's up? Oh no, we still have more. So they're already up on Blackboard. Yeah, I completely forgot about those. Forgot about group assignments. So actually, I have 3 more group assignments for you today. Let me show those to you real quick. Got to talk about them for a second before I give you the test back. So there's this one. So this one is, so the first one says you have 2 electrons are fixed 2 centimeters apart. So basically, here's one electron, here's the other electron. So this is negative E and negative E, and these guys are 2 centimeters apart. And then it says another electron is shot in from infinity and stops at the midway point between the 2. So here is my other electron, shot with some initial velocity v0. This guy's going to move in and stop exactly at the midway point, so that this is 1 centimeter here, and this is 1 centimeter here. And what you're going to use then is the fact that this guy stops, so the final velocity v equal to 0, to then figure out what is its initial velocity. So this is just conservation of energy. That's all this thing is. The second one is this one. So you have a bunch of point charges here for the particular geometry. And what you're looking at is what is the potential at point P. Okay. Now this one is similar to the electric field one that we did before, where you're looking for symmetries, but this one has a slightly different symmetry. Which means that, for example, if I was looking at Q1 here and Q1 here, if I was talking about the electric field, I would say they give no contribution at points P because the electric field lines are equal and opposite to each other. But as far as the potential is concerned, I don't care. Because the potential, remember, doesn't have a direction, which means that the value here from these two would actually end up summing together, not canceling each other out. And the reason for that is because they're both positive charges, which means they both have exactly the same potential at this point. So they would simply sum together instead of subtract from each other. However, these two, where this one is Q3, this one's negative Q3, the electric field from these two at point P would not be 0 because this one has an electric field pointing away. This one has an electric field pointing in. So the total electric field from those two would point in this direction. But as far as the potential is concerned, since the potential is additive, what that means is that the potential here would be exactly the same as the potential from this one, but this one would be negative of this one, which means the two potentials from those would actually cancel at point P. Okay, so you still want to look for symmetries, but be a little bit more careful because now you're not thinking about directions, you're thinking about values, right? So the value has to be the same, but with an opposite sign. But those two, these two aren't too bad. Then there's one more. There's this one, which is basically a lot of the stuff we just talked about. Air-filled parallel plate capacitors, you're going to disconnect it, start adding in dielectrics, and then pulling things apart. So this is actually a very good example for this. Very good practice problem for this particular problem here. So, yeah, so you have 5 overall. So sorry, I forgot that. These are up on Blackboard. So don't worry about that. There you go, David. There, Caleb. Good. That's already up. Yeah, so that's up on Blackboard. The practice is up on Blackboard, and the solutions for the practice are up on Blackboard. So everything is up on Blackboard now. Yeah, I'll just have to get the submission links all set up. Hi, Mary. You're welcome. There you go, Logan. For you, Maddox. Sam, it's nice that the two of you sit next to each other. Lily, for you. Ryan's MIA. Preston, for you. No Thomas today either. There you go, Jackson. All right, so I will see everybody on Monday then. Like I said, either I'll just send out an equation sheets or I'll just make a video talking about each one. But again, we just talked about all that other stuff, so that'd be great. Cool.